One of the cool things and difficult things is that, we're operating in an environment where a very tiny fraction of humans have ever operated or have any experience in.
So at Varda, what we're working on is manufacturing pharmaceuticals in microgravity. What does Varda actually do to achieve that? We build spacecraft that have pharmaceutical payload manufacturing modules inside, ship them up, they manufacture, we then do a reentry and bring a capsule that you see there back to Earth. And inside is a new pharmaceutical formulation that we can then provide to the customers. The personal transition from a SpaceX engineer to Varda engineer was very seamless. So it's like, here's a rocket that all the buddies in the room right now helped build that is deploying our new spacecraft that is being filmed by the camera I designed. It's like, you couldn't design a more fun experience in engineering than that.
So one of the other things is orbital mechanics. And how do you get into an orbit? How do you stay in orbit? Things like that. How orbital mechanics works is actually quite counterintuitive. It's very different than if you get in a car and start driving. You go point that direction, you accelerate. In orbital mechanics, that actually affects the opposite side of the orbit, not where you are right now.
The most common misconception I've found about engineering in space is thinking that space and orbit are the same thing, and they're just vastly different.
3, 2, 1.
You can get to space with a hot air balloon and a natty light can and a GoPro, and you can YouTube those 3 words and you will see a natty light can go to space. That's a little bit trivial. Anyone can do that. Getting to orbit is the tough part. Imagine yourself running off of a cliff and jumping as far as you can. And now let's say you ran a little faster. You could get farther at the end of the cliff. Now just imagine that thought experiment over and over again where you're running faster and faster off the cliff. You're gonna land farther and farther out. Now imagine you take that to the extreme and the Earth's surface is round and it starts to curve out from under you. So that's what orbit is you're falling still, but the Earth is curving out faster than you can fall, and that's orbit. So you gotta be going bananas fast. Like you're going 17,000 miles an hour just by being in orbit. You're going Mach 25. To get to space with the natty light can, you don't have to be moving at all. That's just about altitude. But the key concept here for gravity is that when you get to space and you're not moving, you're not in free fall. It's actually free fall that eliminates gravity. It's not just being high up.
There's just so many things that can go wrong. You're launching into space on a rocket that is very, very loud and it's vibrating like crazy. You're in the middle of nowhere in space, you don't know where you are. You're depending on computers to do autonomous control. By the way, those computers are being bombarded by radiation that causes them to break, stop working.
So you've got the sun, massive fusion reactor, putting out a lot of charged particles and what's effectively gamma dose. Secondly, you've got supernovas. When they explode, they put a lot of particles of very high energy.
The Earth's magnetic field shields a lot of those radiation particles that would otherwise hit Earth. But if you're up in space, then you have to have electronics that can deal with that radiation. We have to have chemicals up there that can deal with that radiation.
Whether it's just basic upsets that you get, or whether it's these big heavy particles that just like blow up your device. And so we have to protect against all those different things in a variety of different ways. You've got extreme temperature ranges. What's actually crazy is because there's no atmosphere in space, temperature isn't really a thing. It's really the temperature that your spacecraft is. And furthermore, you can't design it to work with convection or anything like that. And so being able to work in a radiation-based environment. Relatedly, one of the common myths of space is cold, so it must be easy to make things cool. Not actually true. When you don't have air flowing around you, actually things get very warm. And the sun is always pointing at you, or you're pointing at it. And so that tends to also keep you warm. So actually keeping things cold is difficult, especially for a power-hungry payload like a telecommunications spacecraft.
To stay up there in perpetuity, you've got to be in orbit. And if you're in orbit and you're going that fast, that means in order to come back, you got to dissipate a crap ton of heat. It's something like 2 million hot air dryers on for about an hour of the amount of heat that you need to dissipate in the 10 minutes of going through re-entry. That's kind of the extremes of space engineering.
Also, you're really far away. So, your ability to talk to the thing, you have to close a link over something that's pretty far away. And probably the biggest of all is you can't service, you can't maintenance something that's in space. So you have to design it so that no matter what happens, it'll be able to get into some sort of safe mode that you'll then be able to talk to it, because you don't have that ability to go, oh, that little thing is wrong. I'm just gonna, turn that bolt and fix that. you need really all of the things. You need all the disciplines. You've got mechanical, you've got electrical, you've got software, RF, you've got like many different subflavors of all of those different things. There's manufacturing. How do you put it together? One decision in one particular thing could impact so many other ones. And so, we have to have all our teams really tie very closely together.
Historically speaking, operating in space has been such a constrained environment that it kind of makes engineers go crazy. Okay, you want to put a robot on Mars. Great. Well, your mass budget is laughably tiny. Your power is also constrained. You have less than 100 watts of power, which is not really even enough to light a standard light bulb. Your data is constrained because Earth is 100 million miles away. Materials are constrained because of the corrosive environment. Put all these things into your requirements box and shake it around for a while, and it's just nightmare material. It's a miracle these things work at all.
What you'll start finding with some of the supply chain are unique requirements. So sure, we have exotic materials. That in and of itself is hard. Then you have just mass quantities of maybe raw stock copper and things for propulsion components, which you have to start planning years and years in advance for those long lead times. And so these downstream effects of having rare materials or unreliable vendors drives a lot of new space companies start saying we need to be vertically integrated. Our founder knows that we had to have not just vertically integrated, but everything is co-located. So now I don't have these delays while we're going to California, to Texas, to the Cape, back and forth. I have my machine shop right next to me, next to my test stand. So I'm gonna build it right here. I'm gonna have the engineer here with the technicians. So if work instructions aren't clear, you can pull them to the floor, and then you go out and you test it, you break it, you bring it in, you analyze it, and then you go and you build it again. All of that happens in the same footprint. And so it starts as a supply chain problem, and then you realize you're vertically integrated and you start setting up for success in that way. When you don't have all of this additional infrastructure, engineers are doing 100 different jobs. And so you might be burning people out and you don't feel like you have that amount of support. I think that's something we're really struggling with. And you also have a workforce that doesn't want to stay in the same job. There are far too many people who I thought were phenomenal that dropped out way too early.
There's one pretty crazy thing when we were just, building these different deliveries, batches of spacecraft that we were launching. We spent a couple of really hard weeks getting 26, I think it was, spacecraft built for a particular launch. And we got them delivered, and then we had launch.
4, 3, 2, 1. And we have liftoff of
Went off the pad, basically just barely cleared the launch tower, and then it exploded. What was kind of crazy was that it wasn't that far off the ground, and CubeSats are put into basically missile launchers. It's like super armored Titan case, and so the thing that exploded was the fuel tank, obviously below the payload, and deployers got pushed off and ended up on the beach. Then they ended up deploying out of the containers, and a bunch of them were just sitting there, like waiting to be talked to. They thought they were in space, they were not. And then they, closed them back up and shipped them back to us. And we then pulled them out, and crazy enough, I think every single one of them actually talked to us. Pretty mind-blowing. We were able to negotiate and get a last-minute slot of being able to get 2 spacecraft on one of the upcoming launches. And the catch was, you've got like a week and a half to do it. Fortunately, we had a bunch of piece parts of spacecraft, and we were able to throw that together. And when they got up, we got the data we needed.